Alright, I'm back. Um, I literally just finished recording the sort of first intro lesson to the geometry, and then now I want to talk about lesson 15 in Algebra 1.5 is geometric objects. These are sort of the building blocks of geometry, besides all that logic that I just went through a brief overview of. Again, this is a brief overview. You'll do a lot more with this in an actual geometry class. Alright, and so this lesson is kind of all about geometric objects and relationships, and being able to answer questions based on pictures or sketch the pictures yourself, basically. That's the sort of goals and objectives. And I like to start with this activity usually when I teach this in class. I call it easy words, hard definitions. So define each of the words right here. Using only commonly understood words. Try to avoid ambiguous language. At this time, go ahead and hit pause. And you don't have to write them down or anything, but try to define each of these. Okay, try to define each of these. Okay, assuming you did what you're supposed to do, you just unpause the video, and you're ready to sort of talk about these a little bit. And hopefully you realize that they are indeed easy words, but with hard definitions. Sort of the big idea here is that all four of these are fairly abstract concepts that when you and I talk about and we use the word money, we both know what money means to us as an individual. And until we have a disagreement about money, we just kind of operate on the assumption that everyone else knows what money means, and it means the same thing that we think it means. It's not until there's conflict that we actually stop and talk about these: money, music, love, time. They're all abstract, and in each of these four cases, though, there is kind of more of a concrete symbolic representation. Like money, you have dollar bills, quarters, but that's not really a true definition of what money is. Music is something you hear, or it's the notes on the piece of paper. It's like the sheet music, but at the same time, that's still not exactly what music is. And then, you have love as this sort of very intense feeling, often symbolized with like hearts, for example. But a literal heart is just kind of a bloody mess, which actually is a decent description of love for some people. Moving on, time is maybe the hardest of us of these to just kind of get a handle on, because time is something that we're just sort of subject to. It's that idea of right now is the present, but I have a past and I'm looking forward to a future. Sort of the concrete representation of this is, I guess, a clock. The idea is that none of those things were really all that great of a definition. So you could check a dictionary and get actual definitions for these and see how close you are to the experts, so to speak. Whether you do that or not kind of still gets you ready for this kind of mathematical idea. Can we define every word? Well, clearly no. We can't come up with a good definition for something as simple as money. How are we going to possibly define every word? And so that's kind of a little bit of a letdown for mathematicians. Mathematicians would love to just sort of define everything. But instead we have what's called undefined terms that don't have a precise definition. Geometry is built upon roughly 6 undefined terms. Point, set, line, plane, maybe space, and then 2 relationships on in between. I didn't mean to leave space out of that list. Space could have easily gone in this list. And so this lesson is kind of about working on all of these undefined terms and the relationships between them, basically. So our first undefined term, our first little building block of geometry is a point. It's a zero-dimensional geometric object. It has no size or dimensions, but it represents an exact location. And most of you would agree that, hey, that's point A. Realize that that's actually really, really way too big, that has a definite size, but we're pretending that's a little infinitely small dot. That's called a point. And we just kind of agree that those things exist, even though they're completely a figment of our imaginations. What's a set? A set's like a list group collection of objects, and you're sort of talking about them as a whole. Like a deck of cards, or the volumes of an encyclopedia, a school of fish. Yeah, it's individual fish, but there's also the group. Letters of the English alphabet. Talk about the alphabet as a group, but it's made up of all those individual symbols or letters. So what we start doing in geometry is we pretend points exist, and then we start talking about them in groups. And the first group for points is the points on a line. A line has one dimension length. And so it's sort of like this connected set. It's infinitely long. It goes in two opposite directions without end. And so this is line from A to B, and this is line L. I'll just put this in here as a graphic to emphasize to you that there's basically two ways to talk about lines: using the points or just giving the line itself a name. If you give the line itself a name, it shouldn't really be one of the points on the line. And we're generally going to use uppercase for points, but lowercase single letters for lines. Or you take two of the points, like point AB. So this is the line that goes through points A and B. So when you write that, you will often do it by putting a hat. That's what I refer to it as, on AB. And so a lot of the rookie mistakes in geometry are just putting the wrong hat on things. A little bit more about lines, just sort of get you thinking. There's infinitely many points on a line, but it only takes 2 points to talk about a specific line. So there's all these points just sort of infinitely densely compacted, packed onto the line. But as soon as you talk about 2 specific points, you're definitely talking about the line that connects them and all the points in between or on either side, so to speak. So Mr. Carpenter sort of pet peeve, but I hate the phrase straight line. Lines are straight by definition. If it was curved, we'd call it a curve. The more complicated version of this might be that lines are curves where the curvature is 0. But it's easier to just say, well, if it's a line, it's definitely straight. And if it's curved, we're going to call it a curve. Period. Our next undefined term is plane. A plane is 2D. It's got length and width, but no thickness. It's infinitely thin, and it's a connected set of points that flat surface, and there aren't really edges because it's infinitely large. But we usually just draw it as kind of like a parallelogram or a rectangle, because that kind of looks flat. And so you can name a plane in 2 ways. You can name it using 3 points that sort of form a triangle, because a triangle is the simplest plane you can actually see, because it's got length, width, height, depth. Actually, I said that wrong. It's got a definite length and then a height. It's not got all 3. It's not 3D. It would be bad. Or the other way you can talk about a plane is just with a single letter that's not one of the points labeled on the plane. And so you get into like these 3 points or these 2 lines. Here's one plane. Here's some other plane. A little bit more about planes. A lot of people like to pretend that their piece of paper is a plane because it's flat, but it's actually got a definite size. And it's actually not really flat. As thin as paper is, it's still several layers of atoms thick. So atoms, as small as they are infinitely larger than points. So points are infinitely small. It's kind of crazy to think about. Infinitely many points on a plane, but any 3 points that form a triangle can define a plane. like in this picture. Two distinct lines can also define a plane. Here's two lines that are definitely different, so that's a different plane. Sometimes we'll name a plane with a single letter that's not in the plane. I kind of mentioned that already. Space is even too complicated for us, but we'll take a stab at it. It's a three-dimensional geometric object. It's got length, width, and depth. Some people would say height instead of depth. And for us, we're just going to say it's like all the points that are possible. If you're talking about every single possible point, the place where these lines and points and planes exist, you're talking about space. So a little bit more about space. Just don't worry about it too much and realize it's where everything's going on. So what actually is going on this slide, I can already said this, but I'll point out this picture was one of the earliest mathematical representations of space, in the sense of, I think this is what they thought the galaxy or universe was sort of organized as, was these different types of solids or shapes nested inside of one another. That was fairly wrong, but hey, they were trying. Just a little bit more about dimensionality here. You've got points which are no size, 0D, lines which have length only, so that's 1D, D means dimension. Planes have length and width but no thickness, so that's 2D. Length, width, and depth gets you 3D as space. So here's one dimension, that's part of a line. Here's two dimensions, a square or plane. Here's three dimensions, a cube. And then these are sort of artist's renderings of 4D and 5D. And of course you're having a lot of trouble visually processing what's going on here. It kind of sort of looks like one square nested inside of another. And then you kind of also have to pretend, I believe it, if I remember right, you have to pretend that these red lines are at right angles to all the green lines. So it is kind of this crazy looking thing going on right here. And then here's even crazier. I don't want to even talk about that. Think about it this way. A point's got no sides, but as soon as you drag a point, you would create a line. So you go to one dimension. As soon as you drag that segment then down, so to speak, you get the two dimensions. So you drag a point which you can't even see, it leaves this trail that's 1D. You then take that and drag it, and it leaves this trail, which is 2D. You then take the 2D square and you drag it in this sort of new third dimension, and it would drag out a cube. So to get this 4D, you're actually dragging this cube, so to speak. And that's just really hard to visualize because you're a human, so don't feel bad. We can't define the word on, but we're gonna at least agree what it means. Alright, sorry about that. So what's the word on mean? Well, definition by example, which I hate to do, but sometimes you're forced to do in math. You should avoid it at all costs, but when you're defining the most basic concepts, it's about the only thing you can do. Point C is on these intersecting lines. Points A, B, and C are on line M. And not much better than that. Point B is between A and C. Realize that since there are infinitely many points on a line, there's actually a point between any 2 points on the line. It's an idea sometimes referred to as density in math. So let's do a little quick doodle right here. And blue. Alright, so trying to get down on and between. Here's some line. Let's call it line L. And Here's point A, point B, point C. You can quickly, hopefully, agree with this statement. Point B is on line L between, ooh, that was a little rough, between points A and C. And almost every single one of you just kind of said, well, duh, Mr. Carpenter, of course it is. But realize that you don't really exactly know. What on and between really mean if you stop and think about it. These are sort of undefined relationships. Everybody knows what on and between mean, but we can't really exactly tell you because the words are so simple. We can't make them any simpler. We can't describe them in an easier way. Okay. All right. A little bit more. These are a little more straightforward relationships, and it's easier to talk about what they mean. Colinear. Points M, A, and N are colinear. They're together on the same line. Points T and C are colinear even though the line's not drawn. I could add a line that goes through T and C. Points T, I, and C are not colinear because points T and I are on a line, but clearly C is not on that same line. Throw in a little bit of advanced geometry. T, I, and C make a triangle. Similar to colinear, you've got coplanar. We realize that in both of these cases, the prefix CO means like together. So together on a line, together on a plane. And this one's a little more complicated. Points E, G, O, and B are coplanar. E, G, O, B are on this sort of shaded pink plane. Points F, A, and B, F, A, and B are coplanar despite the fact that the plane is not drawn in the picture. I could add a triangle sort of right in here and it would connect F, A, and B, and I would have added a plane to the picture, but just because I had to add it, or let me say that differently, just because you don't see something doesn't mean it can't exist. Points F, A, B, and C are not coplanar. Let me see what that is. Starting over at this third bullet. Points F, A, B, and C are not coplanar, as B is not on the same plane as F, A, and C. So you F, A, B, C. F, A, C are all on this like lightly shaded blue plane. B is clearly not on that same plane, so they are not coplanar. So here's sort of the first real example on this notes page. It's mostly vocabulary, so here's an example. What are the names of the two planes in this picture? If you look it over, hopefully you eventually settle on, oh, that's not actually labeling any point, is it? And that's not labeling any point. So the names of these planes based on the picture are plane P and plane R. Plane P and plane R. Let's see. Let's clear that. So just sort of keeping track of the answers. Planes P and R. Okay, next question. Which points lie on both planes? Well, if you look at the picture, what points lie on both planes A, B, D. Again, this is just in case me saying it's not enough for you. I'll go ahead and jot them down. Points A, B, and D. Just P in this picture. Well, here's plane P. E, C. So the second half of that question is just plane R. Here's plane R. It's this sort of vertical up and down looking plane, shaded just a little darker. Well, the points that are on this plane but not on the other are F and G. And last but not least, based on this picture, which points are labeled but do not lie on either plane? They're on neither plane, and H's and I are both kind of just floating over here in space. I wish I could resize that, but I don't think I can. So there you go. You look at this picture, you answer the questions. I just noticed that when I typed out the notes page, I didn't use the word just. And so you might have to tweak your answers just a little bit to make things match up. But I'd say you get the general idea. Parts of lines. A segment, or some people say line segment, is the part of a line consisting of two endpoints and all the points between the endpoints. And so here's line L going through points A and B. Well, if you take A and B and you cut off sort of the ends and throw them away, then that would be a line segment from A to B right here. Whereas a ray is the part of a line consisting of one endpoint and all the points of the line to one side of the endpoint. So it's like you go to line AB and you say A is going to be my endpoint, and you cut and throw away sort of this end of the line. This would be ray from A to B. I think I got a little more I want to say about these things. We use the words line, ray, segment, but we also use, I call them again, these hats. So here's the hat for line AB. Here's the hat for ray AB. Here's the hat for segment AB. The only one you have to be careful with is ray, because this says you start at A and go through B. You start at A and go through B. The other two hats for line and segment are like two directional. Before I get to that example, I want to say a couple other things real quick. Segments have definite length. Rays have definite direction. Lines are neither of those. They're infinitely long and they go in two opposite directions. Okay, so that's definite length, definite direction, neither definite length nor definite direction. Okay, so with those ideas, let's kind of look at a picture here, and we're going to find a line, 5 segments, and 3 rays. And so we're going to clear this out. And I think if I put it right there, you can see most of the picture. And we want a line, some rays, some segments. And according to the directions, we're supposed to be able to find one line, 5 segments, 3 rays. 5 segments, 3 rays. Alright, so you look at the picture, and if you look, here is the only line that's actually pictured. And so x to v, and we need the correct hat. V to x, if you switch the order, it would be the same, so I'd accept that also. As for rays, well, everybody probably quickly noticed starting at V going to Z. That's a ray. But what else in the picture is rays? Well, you could start at X, go through V, and just keep going in that direction. You could start at V, go through X, and just keep going in that direction. And so we get to emphasize that direction matters with rays. You see ray XV in this picture, but you also see ray VX in this picture. XV, VX. The first point's where you start. The second point's where you go. So you start at point V, you go through point Z. That's ray VZ. Segments. Now we're back to things that you can name, and the points that you're using as the name can be in either order. But we should still be able to find 5 different segments. And so you get to looking, and maybe the first one you really think of is X to V. Excuse me. Ooh. Erase that. XV. And the big fat points are optional. You don't have to put those on there unless you like them. Now, what about VX? Oh, it's the same, just in a different order. Oh, wait, V to Z and then you stop. V to Z and you stop. Okay. So X to V, V to Z. Oh, okay, Y to X. U to X. So that's only 4. Oh, from U to Y, which would be made up of sort of those last 2 segments that we'd already identified. So there are the things, cat, get your tail out of the way, you see in that picture. A couple more definitions real quick. A couple bullets there that I've already emphasized about order mattering for rays but not segments. 2 rays with a common endpoint, third bullet, that form a line are called opposite rays. And so in this picture, AD and AE are opposite rays. They make a line. And the only point they have in common is the endpoint. Okay, so it's A to D and A to E. They only have the endpoint in common and they make a line. Intersect and intersection. 2 figures intersect if they have points in common. Realize that's a verb. The noun form would be intersection, and that refers to just the set of all points that are in common. Okay? So think we got a quick visual here. 2 distinct lines intersect. The intersection is a point. And so you can kind of look at this cube, and there would be a line that goes through HE and a line that goes through EF, and they would intersect at point E. It would intersect H to E, and F to E would intersect at point E. If two distinct planes intersect, then the intersection is a line. So you've got the bottom of the box, which is ABCD, so plane ABC, and the front of the box, which is plane ABFE. The bottom and the front intersect along this edge AB, so the 2 planes intersect as line AB. Third, if a plane does not lie in a plane but intersects it, then the intersection is a point. Take the top of the box, EFGH, or plane EFG, and think about the line from A through E. Okay, it doesn't lie on the plane that is the top of the box, but it sort of like punches through it right here on what appears to be the E at the corner. Okay, so if you punch a line through a plane, the intersection is a single point, so to speak. It's kind of like the line makes a hole through one point, goes through the plane, and then comes out the other side, which is a little hard to maybe visualize for some of you. So we're going to kind of do that in a second. All right, you don't have room for these examples at the bottom of the page, so I wanted you to draw them on the back of the notes page in such a way to be able to see them. So what I did was I gave it not quite a half fold, because I like to be able to see the name. And then I know I'm going to attach this side. So on top of the fold, I did my little sketches, and we're going to do them together. So here are the 4 little sketches we're going to do. Here. The first one is to draw lines M and N that intersect at point T. So we need 2 lines. And yours would not have to look exactly like this. According to the directions, the names of the lines are M and N. And this point of intersection right here should be named T. And you do a lot of different variations on this picture, but that's the basic idea of lines M and N intersecting at point T. So we clear that one out. Draw a plane DEF and a line GF that is not on the plane. So with practice, you'll learn to draw your planes as sort of a parallelogram. And let's see, D, point E, and point F. Those 3 points are on the plane, and we're going to have a line GF that is not on the plane. So I got to put a point G not on this plane and connect it to F with a line. And so what you're going to get is a line, and we'll draw this dash to show that it's in behind the plane, punching through the plane. It's pretty standard, and I'm sure you've seen it before, to use the dashed line to represent something that you couldn't actually see if everything was solid. Oh, I can't quite get that to show. Scoot it all the way, read it, I guess. Draw 2 segments, XY and YZ, that are not collinear. Draw ray ZX. So we need to connect X to Y with the segment, connect Y to Z with the segment. But those those segments have to be non-collinear. They have to not make a line. Come on, cat. Draw a ray from Z to X. For those of you that have been watching all your videos, you've probably seen the cat grow up before your very eyes. She just gets a little bigger every day. Anyway, so here's point X, here's point Y, here's point Y, there's point Z. Let's see, X, Y, and YZ are not collinear. I think everybody would agree that it's bent, it's not straight. And then we also draw a ray from Z to X. So we start at Z and we go back to X. And we need that to be a ray. And so you end up with something that looks kind of like this. Yours wouldn't look exactly like that, but it's kind of what it looks like. Make sure, by the way, when you're drawing these in the back of your notes, you label what you're going to draw, or otherwise it's not going to make any sense when you look at it later. Alright, last one here. Draw two planes J and K that intersect to form line OP. And this is the one that a lot of people have trouble with, but we kind of cheat. A lot of people just draw them vertical. Okay. And please realize that I can do this a little easier because I've done it many, many times in the past. So that kind of gets you started. And you start bringing this up. It goes in behind here, so it becomes dashed. This would be dashed. For here, it comes out into view. That's not bad. I'll take that. Alright, so let's see. Go back to the description. Two planes J and K that intersect to form line OP. So the name of one of these is J. The name of the other plane is K. And then this line that they're intersecting along is OP. And it doesn't really matter where you put O and P along the line as long as you make it clear that it's sort of the intersection of the two planes. If you have trouble visualizing planes intersecting, seriously think about like where the wall meets the floor. There's an edge that runs between them. That's the intersection, and it's a line. Alright, I think that's about good for now. Again, over 30 minutes of just listening to me talk about some things, but I got to make sure you understand them. Not a lot of calculating required, if any, for this lesson. Thanks for your time. I will see you in class, see you next video. We'll actually feel like you're doing something maybe in the next video. Instead of just kind of going over vocabulary. Thanks again. Bye.